Okay, today we're differentiating logarithmic functions. Now, in the GeoGebra application that we saw that if we have y equals ln x or y equals log to the base e of x, now that function, this is what we just did, that function, this is y equals ln x, okay? So what we did was in our widget, or whatever, or we looked at the function of y equals ln x, and then we looked at the gradient of the tangent to the curve at each point. So when we looked at the gradient of the tangent to the curve at each point, okay, so the derivative function, this is what we found in GeoGebra. We found that the derivative function, when we looked at particular x values, so the derivative function was, so when x was, I think, a third, we had the 3. When x was a half, we had 2. When x was 1, the gradient was 1. When x was 2, the gradient of this function was a half. When x was 3, the gradient of the function was a third. So what we found was that the derivative function was, in fact, 1 on x, okay? So when we looked at the gradient of the tangent at certain points of this function, we did a table of values for the gradient of the tangent at certain points on this curve, and we found that those points made up the function y equals 1 on x. So therefore, if y equals ln x, or you could say log to the base e of x, then dy dx is 1 on x. So the derivative of ln x is 1 on x. Now we're going to actually prove that as well, algebraically. So, is that okay there? So let's look at the proof. If y equals log to the base e of x. Now, I need to differentiate that. We don't have a rule for differentiating it, so I'm going to rewrite this another way. How do I write it with x as the subject? Oh, what can I take of both sides? If I want to make x the subject, take t logs, but no, not take logs, but raise each side to the power of e. So I'm going to go e to that equals e to log to the base e of x. So I'm doing e of both sides, or I can use the log law. And the log law would be that x equals e to the power of y. We did this in prelim, or, because I can never remember the log law, I just say, well, the opposite inverse operation of logs is taking powers of both sides. So because it's log to the base e, you take e to the power of both sides. Now e log e is, it cancels. Yeah, so you just end up with x equals e to the y. Okay, so, or you just use the log law. And the log law is, if y equals log to the base e of x, then x equals e to the power of y. Okay, but like I said, a lot of people forget that law. It's easier just to take e of both sides. So you do one of two things to both sides. You either do power, like you could take, in this case, because it's log to the base e to both sides, but you wouldn't take log of both sides because log is already there. You need to undo the log. Okay, y dx. But at the moment, I've got x as the subject of my equation. I can't do dy dx. In this case, I have to do dx dy. Because normally, where the x is where the y is, and where the y is, the x is normally there. But I'm now differentiating this with respect to y. Okay, so if x is e to the power of y, what's the derivative? What's the derivative of e to the x? So this is what you know. This is what you're familiar with. If y equals e to the x, then dy dx is what? E to the x. So if x is e to the y, then dx dy is e to the y. Good. But I need to find dy dx, so I need to flip this. Okay, so I've got dy dx is 1 over e to the y, okay, which is e to the negative y. What does y equal? Ln x. e to the negative ln x. Doing that there, can I just keep it like that? Which is 1 on e to the ln x. That's better. Let's not do that. It's too complicated. All right, so 1 over e to the power of y. Now y is ln x. So it's 1 over e to the ln x. Now that means 1 over e to log to the base e of x. But didn't we say that e log to the base e just cancels? It's 1 or whatever. It cancels, so you've just got 1 on x. So that's the proof. It's really important that when you see this, e log to the base e of x, that's x. And remembering that log to the base e of e, do you remember these rules? 1 from prelim. Okay, so e log to the base e, they cancel, and you're just left with the x. And log to the base e of e is 1, just from prelim. That is the derivative, so now we want to look at the derivative of y equals ln of function of x. Okay, so if y equals ln of the function of x, just from what you know of doing derivatives of cos of the function of x, sine of the function of x, e of the function of x, wouldn't you just apply the rule, which is what? So remember, here's the rule. If y equals ln x, then this is the rule, that dy dx is 1 on x. Okay, it seems that we put 1 over whatever that is. So what would the rule here be? If y equals log of function of x, then dy dx would be 1 over function of x. But what do we always do when you... What do we always do? If I was doing cos of some function of x, don't I apply the rule for cos, differentiating cos, and times by f dashed x? All right. If I'm doing e to the function of x, my derivative is e to the function of x times the derivative of the function. Okay, so what you do is you apply the basic rule, which is I know that if I differentiate ln x, I get 1 on x, but because this is a function, I multiply by the derivative of the function times f dashed x. In other words, the derivative is f dashed x on fx. But I'd rather you apply the rule and times by the derivative. Okay, so here's our second rule. If y is ln of the function of x, then dy dx is, well, I can just put it like that, f dashed x on fx, or 1 on the function of x times the derivative. 1 on the function of x is applying the rule and times by the derivative of the function. Okay, now we're going to do some examples. To differentiate something that looks like this, y equals log to the base e of x cubed plus 1. Remember, the rule is if y equals equals ln x, then y dash is 1 on x. So if y equals log to the base e of x cubed plus 1, dy dx is, apply the rule, which would be 1 over whatever that is, times the what? Times the derivative. So again, if y equals ln function of x, then y dashed is 1 over the function of x times the derivative. Okay, so these are our rules. If y equals ln function of x, then y dashed is 1 on function of x times f dashed x. So we just get here 3x squared over x cubed plus 1. That's the derivative. Easy. This is the rule you get on your formula sheet. If y equals ln function of x, then dy dx or y dash is 1 on function of x times the derivative. This actually follows that rule because if y equals ln x, you get the derivative is 1 on x times the derivative of x, which is 1, which is just the same rule, which is 1 on x. Okay? Okay, here's another example. If y equals log to the base e of x squared plus 2x minus 1, what's the derivative? Dy dx is 1 over that times what? Yeah, times the derivative of that. Oops. Times 2x plus 2. Now, if you want, on the side, you could go function of x is x squared plus 2x minus 1 for your working out. F dashed x is 2x plus 2. Because you know that the rule dy dx will be 1 on function of x times f dashed x. All right? And so we get, you know what I want to do here? I wanted to factorize it out just in case. 2 bracket what? X plus 1. Do you recognize this as a... No. I don't think we can factorize it. We can't find two numbers that multiply to give negative 1, but add up to give 2. What do we got? Negative 1 and 1. No, it won't work. So you can't factorize that. So you would just leave that. Okay? So, another example here is to differentiate the following. What rule are we going to use? X squared times this. So what rule is it? Product rule. So if u is, what's u? X squared, what's v? Log to the base e of 2x. Okay. So if u is x squared, what's u dash? And if v is log to the base e of 2x, v dash will be 1 over that times, so we apply the rule, which is 1 over that, times the derivative of 2x is 2. Oh, so it's 2 over 2x, which is, oh, look at that, which is 1 on x. All right, so what's our rule? So we're using the product rule. dy by dx is, look, some people want to use VUV with a plus. And so do we want VUV with a plus? Yes, please. So we can, it's either u v dash plus vu dash or vu dash plus uv dash. So we go VUV with a plus, vu dash plus uv dash. See, VUV. Normally I've been doing uv dash plus vu dash, but remember the quotient rule is VUV over v squared with a minus. Yeah. So let's do vu dash today. So we've got, what have we got? Now I would put, so it's that times this, so log to the base e of 2x times 2x. I'd put the 2x out the front because it's going to look strange if you don't. So look, you can write that log to the base e of 2x times 2x, but then you're going to have that with the 2x written on the back. It looks strange. I would, yes, it is that times that, but I'd write the 2x first. Okay, it's always good to put things like x's in front of logs and put it in front of trig functions. Don't put it behind because it looks like it's going to be the log of that as well, or the cos of that as well, or sine or tan. So v, oh look, I can write it this way, look. Log to the base e of 2x times 2x plus x squared times, so I'm just going to bracket that, x squared times what? 1 on x. So what I'm saying here, I would put the 2x in front. 2x times log to the base e of 2x plus what? I've got x squared on x, which is what? Plus x. Now, if you want, you could factorize out the x. You could just factorize out the x because it's a common factor. They do tend to do factorization with product rule, but in this case, I don't think it's necessary. You could also see the answer written as 2 ln 2x plus 1. Okay? I equals log to the base e of 3x over e to the power of x. We're differentiating. Which rule? Quotient. U is log to the base e of 3x. U dash. All right. Can you do the derivatives of those, please? Derivative of this is 1 on 3x times 3, which is, what is it? 1 on x. And the derivative of e to the x is e to the x as well. So the derivative of this function is vu dash minus uv dash over v squared, which is, and we just substitute, vu dash. So it's e to the x times 1 on x minus u v dash log to the base e of 3x times e to the x over v squared is e to the power of x squared. Now, we are going to have to factorize this. We can already see that we can factorize it. Can you see why you can factorize it? Look what you've got all over the numerator and the denominator. There's something that appears in each term. E to the x appears there, it appears here, and it appears here. So you can either, when it appears in those three places, because you've got a term here, a term here, and a term here, you can just divide numerator and denominator by e to the x. Or we can factorize out the e to the x and then cross them off in the next step. And divide each term by e to the x. We'll do, we can see on the numerator we can factorize out e to the x. We'll pull that out the front. What have I got left once I pull it out? 1 on x minus log to the base e of 3x over e to the x squared. Now I can cancel the e to the x from the numerator and the denominator. Can you see why? Because it's e to the x times the bracket over this. So I'll cross out one of those, that with one of these by just crossing off the 2. Are we okay? So instead of e to the x times e to the x on the denominator, I get rid of one of them by crossing out the 2. And I'm left with 1 on x minus log to the base e of 3x over e to the x. Don't put this x down on the denominator because this is a common denominator with the log to the base e of 3x. So if you're going to put and write this as 1 and put the x down there, you've got to add another x up here. You can't put, I would just keep it that way. You probably should. Yeah. So now, the thing here is, they're putting the x on the denominator. What I'm going to do here, I'm going to write it, I'm going to split my fraction up because I've got 1 on x over e to the x and log to the base e of 3x over e to the x. So I'll split it up. So we've got 1 to the x over e to the x. You okay with that? Minus log to the base e of 3x over e to the x. Now, I now can, when you have this, 1 over that over this x now can come down here. I can show you the working out for it over here. So if I've got 1 over x divided by e to the x, isn't that the same as 1 over x divided by e to the x? Yes? So look at this bit. 1 over x divided by e to the x. You okay? 1 over x over e to the x is 1 over x divided by e to the x. Whenever you've got two sets of fractions in one, vertically, change the main division line to a divide by sign. So it's that fraction divided by this. What do I do now? 1 on x times 1 on e to the x, because that's e to the x on 1. So isn't that just putting, you just multiply the x and the e to the x. So 1 over x divided by e to the x is just 1 over x e to the x. Now, if I want to write this with a common denominator, the thing is, I'm missing an extra x here on the denominator. Now that my denominator is x times e to the x, this one does not have an x next to on the denominator. So I'm just going to go times x times x. So which is, and I'll put the x in the front, minus x times log to the base e of 3x over x e to the x. And now I can write it with one denominator. So it's 1 minus x times log to the base e of 3x over x e to the x. So you can put that down there, but it's got, you can put that down there, but it's got implications for this because e to the x is the denominator for both of those terms. So if you're going to put that x down there, you need an x on x here to cancel and go back to 1 in front of the log to the base e of 3x. Differentiate log to the base e of x divided by tan of x. So again, u equals log to the base e of x, v is tan x. Write the derivatives of each and let's apply the quotient rule. vu dash minus uv dash over v squared. Base e of x, or ln x. So derivative u dash is 1 on x. And what's v dash? Derivative of tan sec squared. Okay, so substituting v times u dash, which is tan x times 1 on x minus u times v dash is log to the base e of x times sec squared x over v squared is tan x squared. We've got this, see, within the numerator there's a fraction, so this x has to come down. But if this x comes down now, the x is now a common denominator with the second term. So what do I have to do to balance out? Yeah, put an x in front there as well. Does this make sense? Once I drop this x down here, the first fraction is fine, but by putting the x down here, it means I've made the second fraction over, the second term over x, but it's not meant to be. So to balance that back out, I've got to put an x in front here. So I've got tan of x over x. Now, instead of writing tan x squared, how do I write that? Tan squared x, good. Minus, now that the denominator's got an x in it, I have to balance back up with an x here. X times log to the base e of x times sec squared x. Because if you look at each term, yes, that's fine. And this second term, the x's cancel, and I still have that same term there. All right? Oh, there's a tan x here, there's tan squared x here. Tell me why you cannot go cancelling. There's no tan here. So don't even think about cancelling that with one of these, because you would need a tan there, a tan here, and a tan here to do it. It'd have to be in every single spot. So when we looked at that question before, when we factorized out, this back here, when we look at this example, there was an e to the x here, an e to the x there, and an e to the x there. There's three terms. How do we know there's three terms? Terms are separated by addition or subtraction signs. So instead of me just crossing out, what we actually did was factorize out the e to the x on the numerator, and then I knew an e to the x would cancel with one of these. So you need to have e to the x in all terms on the numerator to cross out with one of the e to the x's on the denominator, right? So to do that, we factorized out the e to the x, and then we knew one of those will cancel with one of these. It's easy just to cross off the two, because that's e to the x times e to the x. So here, but I don't have, I've got a tan x here and a tan, oh, I've got two tan x's here, but I don't have one here. So I can't go cancelling these because I would need to have one here. Now, what people might think, but sec squared x is 1 plus tan squared x. If I did do that here, when I expand, if I replace that sec squared x with 1 plus tan squared x, I'd have to expand the x log to the base e of x with that. I'd still end up with a term with no tan in it. So there's no point doing it. So let's say I decided to try it. I'll just show you why. So we're stopping there, but let's say we continued. We'd have minus x log to the base e of x, watching 1 plus tan squared x over, so that is not, this is not a fraction line. This is continued, don't do this, right? I'll just show you what will happen. So from there, if we went to here, one sec, and then I decided to expand, I would get minus x log to the base e of x. I'm expanding minus x log to the base e of x tan squared x. Because I'm doing, wait, that times that and that times that over. So there's no point me doing this. X tan squared x. The problem with doing this, I still can't, so this is where we stop. We stop here. Because if I do replace sec squared x with 1 plus tan squared x, and then I'd have to expand, I can cancel off a tan x, and a tan x, but not one there. There's no tan x here, so there's no point doing it. There was no point doing it, so you would just go up to here and stop. Okay, you can't cancel unless tan x is in each term. Got it? And terms are separated with addition or subtraction signs.